Okay, today we are learning a new word. It might be new, or you might have learned it last year. It is called enthalpy. It's on page 56. And it says for the purposes of chemistry 11, but we're going to change that to chemistry 12. The reason it says for the purposes of chemistry 11 is because I use this same worksheet with my grade 11s, and I'm like, why rewrite something that's just perfectly good as it is? However, I am going to fix that for you, so I'm just going to make a note for myself to fix that for next time. Okay. Anyway, for the purposes of chemistry 12, enthalpy can be thought of as chemical potential energy. Okay? So enthalpy is sort of equal to potential energy. Now, the reason I say it's sort of equal to is that it really isn't. However, there's no fantastic definition for it that will make sense to you at this point in your lives. Okay? I can read you the actual definition from our lovely AP textbook. Okay. And let's just go and see what it says, because it is a very unfriendly definition. Enthalpy, a quantity defined by the relationship H equals E plus PV. The enthalpy change delta H for a reaction that occurs at constant pressure is the heat evolved or absorbed in the reaction. Delta H is equal to QP. Did we like that? No, thought not. So we're going to go with it as chemical potential energy, but don't go off to university and write that down because it's wrong. Okay, but it's a good way to think about it because it allows you to visualize it. Okay, and it works. And we all know that delta means change in. And so actually, before I say that, we need to get a symbol for enthalpy, and E stands for energy. So E is taken, so we use the H instead. So the symbol for enthalpy is H, enthalpy, which means change in enthalpy is delta H. Now, presumably you guys have heard of endo and exothermic reactions before, am I correct? Yes? Do we remember them, or have we forgotten them a little bit? We remember, we've forgotten, I got some mixed bag there. Okay, so an endothermic reaction, we're going to talk about energy transformations. In an endothermic reaction, kinetic energy is transformed into potential energy. Because I don't know if you guys remember, energy is neither created nor destroyed. It can only be transformed. Yes? Energy can't be created nor destroyed, only transformed. And I'm going to also put or transferred to something else. Okay? Now, if kinetic energy is transformed into potential energy, what is happening to the kinetic energy? Yeah, the kinetic energy decreases. What happens to our potential energy? Potential energy increases, and that one's actually written over here. So the potential energy increases, and the kinetic energy decreases. Now remember, we said that enthalpy, we can think of it as potential energy. So if the potential energy increases, then the enthalpy also increases, because enthalpy, we can think of it like is approximately equal to the potential energy. Now, if something increases, is that a positive change or a negative change? Positive. It is increasing, so the change is positive. So what we can say is that for an endothermic reaction, delta H is positive. Change in enthalpy is positive. So that's endothermic. Now, while we're here, the kinetic energy decreases. What does that do to temperature? Have a chat with your partner. If the kinetic energy decreases, what happens to the temperature? What is temperature? The average kinetic energy of the particles. So just like enthalpy can be thought of as potential energy, temperature can be thought of as kinetic energy, okay? So temperature is the kinetic energy. So if the kinetic energy decreases, what happens to the temperature? It decreases. In other words, this is going to feel, is it going to feel warmer or is it going to feel colder? It's going to feel colder. Okay, now we have an exothermic reaction. And in an exothermic reaction, we are transforming potential energy into kinetic energy. So what is happening to our kinetic energy? The kinetic energy increases. Why am I writing it like that? That looks stupid. Okay, let's just fix that. Increases. There we go. And if the kinetic energy increases, what happens to the temperature? Temperature increases. And therefore it is going to feel warmer. Not feel warmer, feel warmer. All right, now what happens to our potential energy in an exothermic reaction? Sorry, yes. Is enthalpy another word for potential energy? No, but we're going to pretend it is. What does it actually mean? Enthalpy actually means a quantity defined by the relationship H equals E plus PV. The enthalpy change delta H for a reaction that occurs at constant pressure is the heat evolved or absorbed in the reaction. Delta H is equal to QP, which is why we're going to say that enthalpy is potential energy. Okay, because that's just like, If you do take physical chemistry at university, I pity you. It's a horrid, horrid, horrid course. One of my two least favorites, that and linear algebra. Did not like linear algebra. I even enjoyed my physics courses more than I enjoyed physical chemistry. So yeah, that's how well that one went for me. And in my physics course, my first midterm, if you're ever like going off to university and you're worried about like how you're going to do and you're going to feel terrible if you fail, just remember on my first physics midterm, I got 24 out of 50. I got a B. Did I get a B or a B minus in the course? I think I got a B minus. 24 out of 50. Yeah. It depends on the professor, right? But you're going to get people who are like, oh, okay, we just, they're trying to weed people out, right? Because you don't want people who cannot keep up, right? And we don't need anybody out in high school, especially not in the junior grades. We're like, oh, you have a pulse? You passed the course, right? I mean, you've seen it. The kid who sits there and does nothing, and somehow they're in your grade 10 science course next year, and you're like, how did that happen, right? Anyway. Not quite the same in the senior grades, but anyway. All right. So potential energy is now decreasing. So the potential energy decreases, and therefore the enthalpy, which we're going to think of as the potential energy, also decreases. And if it's decreasing, the change in enthalpy is negative because we are going downwards. So it's going to feel warmer. Temperature is going to increase. And that is for an exothermic reaction. So can you think of any reactions which are exothermic? Any reaction at all that you may have seen many, many times in your life where you feel it and it's like, oh, that's warm. Fire. Yeah. Okay. Now, it's a lot harder to think of endothermic reactions where it actually feels colder. One of the things is, those chemical packs where it's like an ice pack that you get at the pharmacy, and you like kind of go like this and it gets cold, so you can put it on if you sprain your ankle or something. It's kind of like an ice pack ready to go for you if you need one. Those would be endothermic, but a lot of endothermic reactions actually require an input of heat because you need that kinetic energy to go in to transform into the potential energy. So like cooking an egg is endothermic. And you're thinking, hey, when I cook an egg, it feels warm. But is it the actual cooking of the egg making it warm? No, the cooking of the reason it feels warm is because there is a oven there, a fire possibly if you've got a gas stove, right? There's a stove there. That's what makes it warm. Okay, it's not the reaction itself. The reaction itself is actually taking some of that heat energy, some of that heat, and transforming it into potential energy. And now it would actually be a little bit cooler than it would if it did not react. Okay, which sounds weird, but you don't have to worry about that too much. Okay. So we are now going to look at where we put this thing that we call the heat term. So when gasoline burns, again, we have something burning. So this is, again, a type of fire. If you have an internal combustion engine, you just have a controlled fire in your car. Okay, if you have an electric car, you've got a different story, but anyway, there we are. So the fuel is C8H18. That's octane, and it reacts with oxygen. So we have the octane reacts with the oxygen, and these guys have a higher potential energy. These are our reactants. Our products, CO2 and H2O, which is why we're trying to cut back on internal combustion engines because they make a lot of CO2, which is, of course, one of our most famous greenhouse gases. So these products have a lower enthalpy or a lower chemical potential energy. So we started with a high potential energy. Okay, so here's the time, potential energy. We started with the high potential energy, and we finished with a lower potential energy. So the potential energy decreased. Yes? Which means that the enthalpy decreased. And we can show that this was a decrease by putting a little dotted line across to our product's potential energy and drawing an arrow from the top line to the bottom line. Okay, so it should touch the top line, it should touch the bottom line, and we're drawing an arrow downward because it starts high and finishes low. And we could label that arrow the change in enthalpy, delta H. I don't know why I didn't connect that properly. Should look more like a curve like that, okay? And look what comes out. Okay, these guys are products, but also heat is a product. Heat is produced. It is released to the surroundings as kinetic energy. So what's happening is you've got the fire. Let's just say we're looking at a fire, you know, campfire, you're looking at it there. It feels warm because the air particles are moving faster, right? And so when they bash into your hand, they bash into your hand with more energy, which makes your hand feel warmer. Yes? And so it is that extra kinetic energy that you feel as heat. Okay? So that's why we call it the heat term, because that heat is being released to the surroundings. And where did that heat come from? Well, we started with high potential energy. We finished with lower potential energy. Can energy be destroyed? No. So what happened to that difference in energy? We used to have this much potential energy. Now we have this much potential energy. It became heat energy or kinetic energy. Okay? Yes? Because I know that fire is an exothermic reaction. Pardon me? Oh, well, I mean, there are ways of doing it. You can go and look up bond enthalpies and do a calculation on it, various things like that, but we're not going to be doing that this year. Okay, we're going to tell you what the delta H is, or we're going to write in the heat term, or we're going to, there's various things we can do, but I'll teach them all to you. Okay, so don't worry about it too much. Okay, so the heat is released to the surroundings as kinetic energy. So heat is basically the kinetic energy. And the particles move faster, therefore the temperature increases. So this kinetic energy term is referred to as the heat term. What kind of reaction is this? Is this endothermic or exothermic? This is exothermic. And if you look at your reaction, is the heat going into the reaction arrow or is it coming out of the reaction arrow? The heat is coming out. So would you say that heat is entering or would you say heat is exiting? Heat is exiting. And what kind of reaction is this? Exothermic. Oh, and you know what? If you have problem remembering that, you can be like, yeah, you can say, when there's a fire, where do I go? I go to the fire exit. So good, right? Because exothermic, fire feels hot. Yes? Heat is exiting, therefore exothermic. So you should be able to put all of these things together. You should say, where does my heat term go in an exothermic reaction? It goes in the products. What is the sign of delta H in an exothermic reaction? Is it positive or negative? It's negative. And you should be able to draw a graph saying in an exothermic reaction, I start, my reactants are higher, and they finish lower in a potential energy diagram. Okay, so all of those, you're going to have some practice relating those all to one another, but that's the general idea. Okay? So here's just a lot of what we have already looked at. This is a bit better of a diagram here. Okay? You can either draw the delta H arrow over here, or if you wanted to, you could draw the delta H arrow over here. But you should always draw a dotted line so you know where it's starting and where it's finishing. That's all there is to it. Okay? Since delta H is negative, we know that the reaction is exothermic, and therefore the temperature must increase. You are never going to have to draw this wiggly kinetic energy arrow, okay? You don't have to draw this. Alrighty. The only reason I put it there is just to show that the kinetic energy, the heat, is exiting, right? It's coming out as the potential energy is dropping. There are two ways to write a reaction to show that it is exothermic. What's one way? Where would you put the heat term in the reaction? Tell your partner. In an exothermic reaction, is heat a reactant or is heat a product? In an exothermic reaction, heat is a product. Okay, so we could write it over here. Now the heat term Often we don't just write heat. We will usually give it a value because it's an energy term. It's given in kilojoules. Okay, so that's our heat term. So we can either write the reaction, actually put the heat term in the equation, or we can write the equation without the heat term, and beside it, we will write the delta H value. One thing I want you to notice about this is when we write it as a product, we write plus 5076 kilojoules because it's coming out. Yes? We don't write plus negative 5076 kilojoules because it's already on that going out side of the arrow. There's no point in saying I am losing negative. It's just weird. Does that make sense? That it's just strange? Yeah, anyway. But when you do write the change in enthalpy, it has to be negative because you're starting higher and finishing lower. Okay? So just be careful of that. Some people want to put the negative sign in the reaction when they put it here, but you don't do that. In the reaction, the heat term is always as plus whatever the kilojoules are. Okay? Okay, next reaction. Ooh, what kind of a reaction is this? Here are our reactants. Is this endothermic or exothermic? Endothermic. The heat enters the reaction. Therefore, this is endothermic. Is this going to feel hot or is this going to feel cold? It's going to feel cold. And your reactants have lower enthalpy, lower potential energy. And the products, because we put in that extra heat, and what happens to the heat when it goes in? Remember, it starts out as kinetic energy, but what happens during the reaction? It changes into potential energy. So kinetic energy is absorbed and converted into potential energy. That's going to make the particles move slower because their kinetic energy drops, and that's going to mean our temperature decreases and it feels colder. All right, so let's just draw a quick little graph of this. What do you think our potential energy diagram would look like for this? Yeah, we're going to start low, lower potential energy, and then we're going to finish higher potential energy. These are our reactants. These are our products. What if we wanted to label delta H, our change in enthalpy? We're going to say either you can put your dashed line here and say here, all the way from one line to the other line, don't stop short. I get really irritated when people do this and they're like, delta H. I'm like, what? Right? Like draw the line from here to here, please. Okay, it's not difficult. Or you could put it over here if you wanted to. Either way is fine. Shouldn't go past that. I'll pretend that goes down there. Okay. So heat is absorbed from the surroundings and converted into enthalpy. Oh, I should label that delta H. Okay. Here is an enthalpy graph for this reaction. Here comes our kinetic energy. The heat enters the system. And is what happens to it when it goes in? It is changed into what? Potential energy. And therefore, our potential energy increases. Our delta H. What sign is delta H? What sign is it? Positive or negative? Positive. Delta H is positive. So because delta H is positive, we know the reaction is endothermic, and the temperature must be, or sorry, the temperature must decrease. In an endothermic reaction, the heat term is written in the reactants. Heat enters. And delta H is positive. So we have those two different ways of writing the reaction. You can put the heat term in the equation, or you can put the heat term, you can put delta H separately on the side. Okay? What time is class over today? We got 5 more minutes, right? Yeah. Okay. Oh, and look, there's exercises. That's perfect. So I'm going to have you do those exercises here. I'm also going to have you watch a video over the weekend. I will post it on Teams. Okay? So your homework is pages 59 to 60. And check on Teams for a video to watch. Or 2.
Did we supposed to read this?
Yes, you were supposed to have read that one. Yes.
I'm fine then.
Okay, yeah. 1.3, read and do it. Okay, also, if you didn't do 1.3a, what pages is that? 51 to 54. If you've not done 51 to 54, please do.